Hi, welcome to another video on math problem solving. Today's problem is one with a perfect square. Let's get started. Prove that the sum of 5 consecutive perfect squares can never be a perfect square. So what's a perfect square? A number that can be written as the product of another number multiplied by itself. So an example would be 16, which is 4 times 4 or minus 4 times minus 4. Giving you 16. So 16 is a perfect square. So is 25, so is 36. So how do you go about proving this? Now, remember, we are all about productive struggles. So unless you attempt it, you really won't be able to appreciate the solution. So my suggestion would be to pause, try it out for a few minutes, and then get back. Okay, so I'm going to be doing the answer in 3, 2, 1, and let's get started. So here's the assumption. There's a clear-cut, straightforward algebraic method of doing this, and if you know how to do it, then you're there. But this video is designed more to help you analyze the problem for someone who really can't figure it out, who doesn't know the method. So in that case, what do you do? Because maybe you might be one of those people who could solve it straightforward because you have an intuition for this problem. But tomorrow you might see another problem where you don't have the intuition and you're struggling. So this is more of a methodology to help you think about different ways of doing it and not really jump into a solution and get lost in the algebraic soup that follows. So my suggestion would be to start empirically. Think about writing down all the squares. For example, the smallest one I can start with is probably 0, but I'm starting with 1. So 1 square is 1, 2 squares 4, 3 squares 9, 4 squares 16, 5 squares 25. Add them up, I get 55, which I know for a fact is not a perfect square, but I know it's between 49 and 64, between 7 and 8. Okay, let's keep that in mind. Let's try another one. So 2, 3, 4, 5, 6. I have the perfect squares as 4, 9, 16, 25, and 36. The sum is 90. Again, it's between 9 and 10. 9 square being 81 and 10 square being 100. But definitely not a perfect square. So let's collate this. But before that, how about starting with a random number? Maybe I can begin with 7, 8, 9, 10, 11. Add them up together. 4, 15. Again, I am nowhere near being a perfect square. So let's collate all of this together. So let me put down all the first number of a set of 5 numbers that I'm considering. The sum of all the 5 squares. So for example, if I'm taking the use case of 2, then it's 2, 3, 4, 5, 2, 3, 4, 5, 6. Add them all together and you get 90. Now, as you can see, for almost all of this, the 8 use cases to begin with, none of them are perfect squares. So the statement holds some truth. And in fact, if you look at the difference between them, there's a pattern to it. So it's 25, 35, 45, 55, 65, 75, and 85. So fairly interesting. You won't find the solution right away, but you can at least see that, hey, trying it out with some of the basic empirical values does not give me a perfect square. So there must be some truth to this. But remember that you need to prove it for whatever number. It could be 1 as the first number, or 1 million, or 1 billion. You still be able to solve it. And the only way to do that is an abstract solution. What's an abstract solution? You don't know what the first number is going to be, so let's call it n, which means the square is n squared. The next number we know is n plus 1. So when I square that, I get n squared plus 2n plus 1. The number after that is n plus 2. The number after that is n plus 3. And finally n plus 4 when squared, giving you n squared plus 8n plus 16. Doing a similar addition would give me 5 times n squared plus 20 times n plus 30. What do I do with this? I know that for a generic n, I really don't know what that n could be. It could be 1 or 1 million. But that generic n, and if I have the 5 numbers from n plus 1, n plus 2, n plus 3, n plus 4, square all of them, add all of them, and I get 5n squared, 20n, and 30. How does this help me? So I need to factorize this a little bit. This is where the mathematical wizardry comes in. I know that every one of those numbers, every one of those terms in this algebraic expression is divisible by 5. So I take 5 out, I'm left with n squared plus 4n plus 6. I need to turn this into a perfect square. So I divide the 6 as 4 plus 2. And then I get in 5 times. So 5 is the first term. The entire second term now is n plus 2 whole square plus 2. So what do I do with this? As I said, this term is what needs to be a perfect square for our proof to work. So term 1 is 5, term 2 is n plus 2 whole square plus 2. Now, this is where logic comes into play. Now, if this entire term 1 times term 2, if that needs to be a perfect square, then term 2 should be a multiple of 5. Why? Because term 1 is just 5 alone, and 5 is not a perfect square. So it needs to find a pairing 5. Term 2 can be anything more than that. It could be 5 times something else. But it needs to be a multiple of 5. This is absolutely necessary and logically very, very consistent. But how does that help us prove whether it's a perfect square or not? So we have this term, this is term 2 for us, should be a multiple of 5, let's accept that, which means n plus 2 whole square plus 2 needs to end in 0 or 5. When I subtract the 2, that particular value, n plus 2 whole square, has to end in 2 or 3. Now, we know that n is a number, an integer, a natural number, which means n plus 2 is also a natural number. And that is squared, giving you a perfect square. But remember, no perfect square ever ends in 2, 3, 7, or 8. Because if you take the numbers from 0 till 9 and you square all of them, you would realize that none of them ever end in 8 or 3. Which means if this particular term 2 is actually divisible by 5, then n plus 2 whole square has to end in 8 or 3, which is impossible given that n is a natural number. And therefore, that inconsistency leads us to the conclusion that term that we started off with, which is 5 times n plus 2 whole square plus 2, can never ever be a perfect square. Now, of course, there's a more elegant solution. You can rewrite, whenever you think of 5 consecutive numbers, you don't start with n. You in fact start with n minus 2, so that you find a symmetry to the whole thing, making this very, very elegant. You don't have 3 terms, you just have 2 terms. It's 5n squared plus 10. Again, you have the same thing, which is 5 is a common factor. You take that out, you're left with n squared plus 2. This needs to be a perfect square. For this to be a perfect square, term 2, which is n squared plus 2, needs to be a multiple of 5. And therefore, we can come to the same conclusion that it has to end in either 0 or 5, if it's a multiple of 5, which means n squared needs to end in 8 or 3. And we know that n is a natural number or an integer. And it can never ever have the square of itself ending in 8 or 3. And therefore, you can conclude that the sum of the 5 perfect consecutive squares will never be a perfect square itself. What's your next step here? If you like this proof, you shouldn't stop here. You should go into an exploration mode and say, okay, the question specifically says sum of 5 consecutive perfect squares. What if it's sum of 2 consecutive perfect squares? Is it possible that then I could have a perfect square? The clue here is Pythagoras theorem. Yes, 3 square plus 4 square is actually 5 square. So 2, I have kind of helped you out. But can you think of 3? The 3 numbers would be n minus 1, n, and n plus 1. When you square all of them and you add them up, what do you get? Can you prove or disprove that this would be a perfect square? Or is there a possibility that at least one such combination can get me a perfect square? What about 4, where I would have, n, n minus 1, n plus 1, and n plus 2? Might not be so symmetric, but if I add all of them, is there at least one value of n for which it would be a perfect square? When you spend some time exploring all of this, this is how you would get into a productive struggle mode, and that is how you would build your mathematical mindset and capabilities to solve many such math problems, where you can actually not only take just recognizing patterns the way we did with our empirical solution, but also extend it into an abstract solution and actually apply logical reasoning to be able to prove and disprove things which is often the bread and butter of higher level mathematics and Olympiad level math. I hope you found this video interesting, useful, and if so, please share, subscribe, and click on the bell icon, and I will see you in the next video. Thank you so much.